Kali.
Hello everyone, this is Yasa Arafat taking you through Boolean functions and expressions. That is chapter 5, elements of mathematics, section 5.5, 5.6. So I'll define a Boolean function by saying that if b to the power n tends to a b where b is equal to a 0 and 1, but remember each variable has a maximum, or it can take on two values, meaning that I will have 2 to power n possible input combinations. I'm having 2 to power n because I'm having n variables. But remember that for each input combination, the output is either a 0 or a 1, which implies that I will have a 2 to power 2n possible Boolean functions as my output. For example, if my n is equal to 1, I will have 2 to power 2 to power 1 possible Boolean functions, which implies, you see, it is a 2 . So I can have 4 Boolean functions if the variable was 1. Assuming I had n as 2, if my n was 2, that means I will have a 2 to a power 2 to a power 2, and the output is, this is a 2 to the power 4, which is a 2 to the power 4, which is 16 Boolean functions from that. So basically that's how I can get the Boolean functions given any variables. So we can proceed to the canonical forms, and I'm saying that every Boolean function can be expressed in 2 canonical forms, i.e. the sum of products and the product of sums. So here I quoted it in the bracket that the sum of products, it is also known as the sum of many terms, and the product of sums, it can also be referred to as the product of max terms. There is an NB here where I say that min terms are written when the output is high. That means the output, when it is 1, I will write the mini term, implying that I will get the max term when the output is low, which means that the output should be a 0. We shall refer to this NB when we are coming up with an expression of the Boolean function. So here we can talk about the min terms and the max terms. I'm saying that a min term is a product of any literals in which each variable appears exactly once, either complemented or uncomplemented. We shall apply this definition and we see what are the literals. Complementation, we shall refer to these examples. So a max term is the sum of any literals in which each variable appears once, either complemented or uncomplemented. The examples, I'm considering the function f is xy, but since this y has a complement on it, which complement I can read as a prime, and sometimes we may write it as a y bar, but the implementation is 1, y prime, y naught, or y complement. So this is xy naught. All, because according to Boolean algebra, the plus is, we interpret the plus as all. So this is xy naught, all xy naught z, all not x y z w all x, not y, not z. So this is the function that we have. Basically, what do we want to interpret from here? Let us get the literals. So literals, they are just the variables in each product. So here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have 12 literals. So I'll say that the literals are 12. So after getting the literals, I need to identify, is this a sum of products or it is a product of sums? So depending on our definitions, I am having a mean term, but remember I said that a mean term or the sum of mean terms, it is also the sum of products, which implies that I'm having a product here plus a product here plus a product here plus a product, which implies that I'm having a sum of products. Therefore, F is a sum of products. F is a sum of products. F is a sum of products because I'm having a product plus a product plus a product plus a product. Therefore, it is a sum of products. So, here we say that to identify a mean term, I will need a product, but that product should include all the variables that are in this problem. The product should include all the variables in this problem, but the variables should either be complemented or not complemented, provided they are all in that term. So here I will identify the mean term. So here, let me first identify the variables that I have. The variables in this problem, the variables in the problem, I'm having x, there is x, there is y, there is z, and there is w. So these are the variables that I have in this problem. What do I now I want to identify the mean term, but I'm saying that mean term should have all these variables. That term should have the x, should have the y, should have the z, should have the w, either complemented or uncomplemented. So this is the problem. Here I have only x and not y. This is x, y, not z. This is x, not x, y, z, w, implying that this one will be the mean term. So I'm taking this one as the mean term because it has all the variables included. There is x, there is y, there is z, there is w. So I'll say my mean term equals not x, y, z, w. So that is the mean term. I'm taking this as a mean term because it has all the variables included, either complemented or uncomplemented. So I have here another example, and they're telling me to consider the expression f is equal to bracket x or y, close the bracket, another bracket. So what do I identify here? There is a product. There is a product. There is here a product. So I'm having this term multiplied with this term, multiplied with this term, multiplied with this term, implying I'm having, but this term is a sum because this is x plus y, so it is a sum. There is a multiplication symbol here, and this is also another term which is not x or z. A multiplication symbol, this is y, all not z. A multiplication symbol, this is x, all y, all not z. So these terms are being multiplied, which implies that this is a product of sums. So this is a product of sums because this is a sum times this sum times this sum times this sum, implying that f is a sum. It is a product of sums. F is a product. F is a product of sums. F is a product of sums. What else can I identify from this problem? I can get the literals. Remember, we said the literals are just the variables in each term. So here, I can get the literals. How many literals do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9. I have 9 literals there. What else can I get? But remember, this being a product of sums, so I can get the maxi term. I can get the max term because here we say that if it is a product of sums, you can refer it to as a product of maxi terms. That's why I'm saying that I can get a max term from this problem. So how do I identify a max term? We say a max term should have all the variables included. The variables should be there, either complemented or uncomplemented. The same way we got the mean term. To get the mean term, we say look for that term, but that term should be having all the variables, either complemented or uncomplemented, but that term should include all the variables. It is the same thing that I'm applying here. I'm looking for the term, but the term should be having all the variables. So that would be the maxi term. So this is the first term having x all y. This is not x all z. This is y all not z. This is x all y all not z. Implying that this term is having all the variables included. Meaning that x all y all not z is the max term. So it is the max term because all the variables are included and it is a product of sums. So I'll proceed to the algebraic simplification. The algebraic simplification of Boolean expressions. So I summarized these laws because they are to be discussed in the previous sections before this one. So I had to summarize them. So this is the AND gate rules, the OR gate rules, and others. For example, the distribution law. And we use these laws, or the Boolean laws of algebra, in simplification of Boolean expressions. The AND gate rules, this is A and A. A and A, I get A. This is A, all A, I get A. A and A naught. A and A naught is a 0. A and A naught, it is a 1. All, this is A, all, not A, which is 1. This is A and 1, which is A. This is A, all, 1, which is 1. This is A, all 0, which is 0. This is A. This is A, all 0, which is A. Others are there. We shall apply those ones during the simplification of these expressions. So this is the first example. F is equal to A, B, C, all, not A, all, A, not B, none. This is A, not B, C. So we have simplified that one problem using Boolean algebra. Step number 1, I will have to factor out the commons. For example, here I'm having A, B, C. Here I'm having A, not B, C. Implying that SC are common to these terms. So I have to factor out My A is equal to, what am I factoring out? It is AC. So I have AC into, here I remain with B, here all, here what do I remain with? Not B, all not A. So this is where I am. Now I can refer to these rules. Which rule says that B all not B? What is its equivalence? I'm having A all not A being 1, therefore B all not B is 1. So I have my function A, C. This is a 1 all not A. So that's where I am, which I can simplify to have it as SC all not A. Members, I'm using a bar just for convenience purposes. I find it for convenient using the bar, but it is okay if I use a prime or a complement. Okay, but I'm using a bar. I'm saying a bar because it is convenient for me when I'm writing it. So this is where I am, but I can further simplify this using the distribution law. I had noted them here, which is this one. So I'm having not A all a C. And here they are telling me that not A all a B, it is the same thing as not A all B. So I will have to further simplify this by saying that this is the same thing as not A all C. So that is the simplified solution to that problem. I have another example here. Example number 2. F is equal to AB all not SC all BC. So you can still further simplify this problem using Boolean algebra. I'll say that F is equal to, this is AB all not AC all BC. I have introduced what I can refer to as a neutral term. The neutral term is not A all A. So in other words, I've not changed the question. This is not A all A, but I can still refer it to this one because if I have A all not A as 1, implying that here I've just introduced a 1, silent 1, which has already been there. But I've just represented it as not A all A to simplify this problem. So I'll still need to, I'm going to apply the law of distribution on these two terms. So if I apply the law of distribution, this is not A, let me use bar. It is not A, B, C, all A, B, C. So what else? Which terms have the common members that I can factor out? Let me see. Yeah. So this is AB, all not A, C, all not A, B, C, all A, B, C. So still, so in these two, I can factor out something. And similarly to these two, this one and this one, this one and this one, let us have it as not A, C, a 1 plus, here I have a b, 1 whole b, this is from these two terms, then these two, I have all, this is ab, this is ab, into, so here I have a 1, and here all c. So I think I can further refer to my rules because they are telling me that a all 1 is 1, which implies that this is a 1 and this is also a 1. Therefore, I will have not a c all a b. Not a c all a b as a simplified Boolean expression. So I have number 3 and number 4, which someone can try out, and these are the expected answers for number 3, and for number 4, the answers are there, the ones that are expected.